Swayam Prabha. Digital India. Educated India.
So this is the topic that I'm trying to brief you here. Actually, it runs from, it starts from mathematics, and from mathematics, this is applied in physics, chemistry, and also biology. The applications are in, basically, it is a physics principles. And it is coded with the help of the computer scientists or who can code, who can program it. Very complicated equations are integrated and differentiated and so on computationally, and it is applied in various branches of science: physics, chemistry, material science, whatever. For me, everything is physics. And the chemistry, biology is also chemistry. All right. So this is, please come. So this area, this topic that I'm covering will have all concepts put together, and we have applications in various fields of science. All right, and in science and technology also. So I thought that I will brief you with some ideas of this. Alright, and that's why I put the principles and applications of molecular modeling. The application that I am going to pitch here is drug discovery. Maybe Dr. Chaitanya or Suraj or somebody who is going to come here, they will brief you about some properties. How do you get some properties? How do you predict properties? Alright, maybe with this techniques. And I thought I will stick to classical, little bit of quantum mechanics, right? Not heavily on quantum mechanics. Definitely, Professor V. Balakrishnan will be coming and he will be talking to you on quantum stat mech and that kind of things. Right? I thought that I won't bore you with a lot of quantum mechanics, but I will make use of little bit of quantum mechanics. All right. And apply it here and show you how this is utilized by the chemists and physics and also biologists today to understand various ideas. Alright, and apply it in various fields today. It is a very broad field today. Basically, we are all familiar with the very simple equation, right? But involved in many ways. Alright, what is this equation? Force equal to mass into acceleration. We are all familiar with this equation. Alright, and this acceleration is, you write it as rate of change of velocity, and rate of change of velocity is nothing but rate of change of displacement. Right, you are all very good kids because we know that. Therefore, this is nothing but, let R is the displacement vector, right? Then the rate of change, then velocity, we know from calculus, rate of change is dr by dt. Therefore, this is simply dr by dt, this is velocity. Then your acceleration is what? It is dv by dt, and this is equal to d square r by dt square. So we are all familiar with this, right? Any question? Right? Simple. So what I have is this f, right? F is equal to m into d square r by dt square. Let me, for the if wherever it is necessary, I will put vector. Otherwise, you assume that it is a vector. You are all familiar with the vector quantity and so on. Now, this is a very important relationship. We are all familiar with this. Nothing new about this. The next step is, we are all familiar with the energies. One is your kinetic energy. Kinetic energy is half mv square, alright. So this is p square by 2m, and potential energy is attained by the body by virtue of its position, therefore it is mgh in some height, alright. So you have a kinetic energy and potential energy, alright. So what's something special about what is work done? So we are all familiar with the work done. Work done is force into, suppose I make a very small displacement dx, right? I consider point x at with reference to the 0 or with respect to the origin. I consider point x and another, and it makes a small displacement x plus dx, right? So that because of some force F is acting on it, because of that force you have this, some work is done, that work is done is given by this W equal to integral F into dx, force into distance, that's the. So you can this quantity resides as work done, resides as potential energy. Yes or no? How many of you are familiar with this statement? It's the internal energy, potential energy, right? The work done resides as the potential energy. Therefore, we are familiar with this. Now, what I am going to do is, so this, therefore, my forces, so this resides as a potential energy, therefore, my potential energy is a derivative of potential energy. This resides inside, therefore negative. Therefore, this is force. So, negative of potential energy, derivative of the potential energy is your force. Alright. Then connect these two equations. So, I have this equation, F is equal to m into d square r by dt square, it's a vector. And this is also equal to minus dv by dx, alright, or you make it as dv by dr, right, clear? If you have a one-dimensional system, let me call it as a one-dimensional system, alright, you consider the momentum only in this direction, x direction, alright, my force will be mass into d square x by dt square minus it is dv by dx. Actually, it is partial. I can make it as partial also, or make it as r. Let me leave it as such. So it is minus dv by dx. I am sure from vector algebra, how many of you you have done vectors? Right. So you from vectors, we know that any vector can be represented as a1i plus a2j plus a3k, where I, j, k are the unit vectors in the three mutually perpendicular directions along x-axis, y-axis and z-axis. Any vector with respect to the 0 can be represented in terms of a1, a2, a3. These are the components in x, y, z directions. Therefore, any vector can be written as a1 plus a2 plus a3. Right? Now, I have a function which is I have a function u which is u of x, y, z. Alright. Then how many derivatives you will have? You will have partial derivative with respect to x, y, z. So, while taking partial derivative, what you will do? You will keep yz constant here, you will keep zx constant here, you will keep xy constant here. How many of you are familiar with the partial derivative? All are, right? Right. Then you can have a second order partial derivative. Dou square u by dou x square, dou square u by dou y square, dou square u by dou z square. Then the combinations, yes or no? Alright, then we are familiar with this theory. this equation dou square u by dou x. Yes or no? Equal, right? Yeah, we are familiar. Now, using this partial derivative, we can define a operator, right? I dou by dou x, j dou by dou y, k dou by dou. Have you seen this operator? D by dx is a differential operator, yes. Alright. A vector operator written like this, it's a del operator, I dou by dou x plus j dou by dou y plus k dou by dou z. Therefore, it's a combination of the partial derivative in x, in y, in z. In all these three axes, you have a partial derivatives. Now, this quantity, if you look at this, this quantity, it's a vector quantity, right? Therefore, this will have this r is a function of x, y, z. Therefore, this will have a component xi, yj plus zk. So, my dr by dt will be what? I into dx by dt plus j into dy by dt plus k into dz by. Alright. So, your d square will be the second order derivatives, you are all familiar. But if you look at this, this is dou v by dou x, I dou v by dou x plus j dou v by dou y plus k dou v by dou z. So, this is the three-dimensional. I consider one dimension now. I write this equation in 3 dimensions. Alright. My equation force equal to m into a. Force is equal to m into d square r by dt square. Alright. My m into d square by r by dt square equal to minus del v. Del is the operator which I have defined already. I dou by dou x, j dou by dou y plus k dou by dou z. And V is the potential energy. So, the solution to this equation m d square r by dt square minus del V is attempted in this lecture. My entire lecture purely depends on this quantity, alright. What I am going to explain you here is only this, nothing else, right. M d square r by dt square, this vector quantity is equal to minus del V. The solution, this is a differential equation. How many of you are familiar with the differential equations? 1, 2, 3, all. How many of you are not familiar with the differential equations? You have done differential equations or not? You are from that Vidya Mandir school, right? Yeah. I remember your face. You have not done differential equations? Differential calculus? Integral calculus? Later. How many of you are not familiar with the differential calculus and integral calculus? You have done integral. Equations. Only differential you have done. Right. Anyhow, basically what we have to do here is, so when you have something like this, dy by dx equal to 2x. Alright, this itself is a simple differential equation. So dy by dx, then dy equal to 2x can be write like this. Then what I will do is, the integration is the reverse process of differentiation. Alright, therefore what I do, I will integrate like this. Alright, geometrical meaning we can talk more, but this is not my cup of tea today. Alright, therefore integral dy is y. 2 is a constant, it comes out. Therefore integral x dx, right, 2 into integral x dx will be, there's a standard formula is there, x to the power n dx equal to e to the power xn plus 1 plus c. This is the formula. Therefore if you integrate x dx, you will get a x square by 2 plus c. So y is equal to 2x square, not 2x square, x square plus c. So this is the integration. Whatever that you have in differentiation, the reverse will be the integration. At this moment you can assume like that, and then we can write the general formula. So basically what I am going to do here is, I am going to solve this. I am not going to explain how we solve it, alright, but we are going to solve this for molecules. My idea is, I said it is principles of molecular modeling, right. Therefore, I am going to solve this equation, right, for molecules, right. What I am going to do here is, I will explain you what is, now the basic mathematics behind this only this. So, what is meant by molecular modeling? So, we are all familiar with the models, right. We see several advertisements, several models comes and advocates about particular product and so on. This itself, this area itself is a modeling, right. But no, they do modeling to sell the product here, but here we want to understand, predict the properties of certain molecules. Model is defined as a simplified and idealist description of a system or a process, often in mathematical terms. In fact, today somebody said that he is interested in deep learning and AI and so on. Today in molecular modeling, AI is one of the important components, right. So the molecular modeling means that it's an idealized description of a particular molecule or behavior of a molecule or a particular process or the chemistry of the molecule in terms of the mathematical terms. Basically what we want to do here is, if chemical reaction is taking place in a test tube, what will happen is, you have a chemical and you have a B chemical, both A and B are put together in a test tube, right. What will happen? They move towards each other. Therefore, the movements of the molecule is fundamentally important. The time evolution of the particle. What is this equation? This is basically gives how a position vector of a point moves with respect to time, which is represented in terms of its potential energy. So, m into d square r by dt square physically gives you information about how the particular particle moves in a potential, right, which is described by this del B here, right. Therefore, this is the basic equation which tells you that how two particles moves in a system. Therefore, that is the idea here, right. So, we want to solve this equation for a molecule. Therefore, we need to define what is the molecular potential energy, alright. Potential energy of any particle is V, and we have to find what is V here, alright. Molecular modeling is concerned with ways to mimic the behavior of the molecules and molecular systems or collection of molecules. This is called molecular modeling. Let me move. What are the scales of molecule? What kind of information one can get? Which molecular modeling tool that one has to use? Alright, that's the idea here. So, for example, there are several phenomena which are taking place in chemistry and physics, which is of the order of 10 power minus 15 seconds. What do you call this 10 power minus 15 second? It's called a femtosecond. Alright. suppose I have, let's take this simple molecule, alright. I am not a good chemist or a physicist, alright. So, I have CH4 and CH4 is interacting with something else, alright. H goes and then you get a something like product you are getting, alright. Now, what happens here, we have to look at it here, when these two interact, right, when these two interact, this H has to go and this X has to come in. Therefore, what you have two kinds of phenomena, one is bond, another is bond making. So, what is the time period with which this bond is formed and bond is broken? What is that? Very small. That very small, you call it as 1 femtosecond, which is nothing but 10 power minus 15 second. It's called a femtosecond. So, you can model this experimentally as well as theoretically. Oh, Nanna Kuttai Udra. What's your name, da? Enachu, Nanna Saptiya? Very good. Coffee special alright. So, you can, if certain things are happening, bond breaking and making, alright, in this kind of time, the time at which bond is made and formed and broken is 10 power minus 15 seconds. And if the dimension, you know that what are the dimensions of the molecules? Are you familiar with the bond length and bond angle? Right, CH4, that's why I gave a CH4. What is the bond angle in CH4? Right, what is the bond length? Bond length. What picometer? So, if the bond length, CH bond length is of the order of 1 Armstrong unit. Alright, 1 Armstrong unit is what? 10 power minus 10. Alright, the CH bond is of the order of 1 Armstrong unit. Therefore, if the dimension, then the molecular dimensions will be of the order of Armstrong units. Alright, if the molecule dimensions are Armstrong unit, then the kind of a mathematics that you apply or the physics that you apply is quantum mechanics. Alright, slightly larger. I have several thousands of atoms, lakhs of atoms, right, aggregation of proteins. Then I can apply quantum mechanics, alright, then I apply classical mechanics. What is classical mechanics? Classical mechanics is nothing but your Newton's. Excellent. Newton mechanics is your classical mechanics. Therefore, you use F is equal to ma relationship. Therefore, F is equal to ma will be used by all of us to understand what is the physics associated with this particular process. That's why I gave an example of a protein here. Right, then still larger system. Then we use Monte Carlo, still larger system, right? Then we use mesoscale, still larger, then we'll use a continuum simulation or continuum mechanics and so on. Therefore, my expertise lies in this area, quantum mechanics and classical mechanics, where we look at the various kinds of process. Specifically in recent times, in the last 10-15 years, I have been working on certain aspects of the proteins and their interactions with a variety of molecules. That's very, very important from biology point of view. How two proteins are interacting, this is called protein-protein interaction. How a protein and a ligand is interacting, this is called protein-ligand interaction and so on. Alright, so these are very, very important interactions. Alright, you are from GEM school, right? Which school? IIM. Right. So what I am going to tell you here is what is meant by, we have a mechanics, whatever that I described as a mechanics, alright. Then what I am going to talk to you is about something called force fields. And then I am not going to give you all these information, but I will straight away go to what kind of information one you can derive. Alright. So now with the reference to the molecules, alright, let me explain on the board so that you can understand more easily. How many of you are familiar with harmonic motion? Right? What is the harmonic motion? Can you tell me? Needampa. Yes. உட்காந்துட்டே பேசு சத்தமா பேசு.
In a general way, harmonic motion will be when it is in terms of the motion can be described in terms of sine or cos with respect to time.
Right. Anything else? Excellent. Any other important property? Huh? Right. కొంచెం నేర్తుంది நீங்க சொல்லுமா. So then anything else other than excellent, that's very important. Then it is a restoring force. Yeah,
it has a restoring force which is directly proportional to the displacement.
It is a restoring force directly proportional to the displacement. That's what she also said. Right, about the mean position it makes. Anything else other than that? Huh? That's what he said. Right? So everything put together, alright, very important point. This is a very, very important point. So your displacement d square y by or dy by dt, right? Directly proportional to, or how do you write? D square y by equal to minus a y. Yes or no? Correct? Yeah, this is, she said that the d square y by dt square, this is, what is this quantity? Yeah, acceleration is directly proportional to r. Yeah, so this I have a point here and it goes like this and comes back. Therefore, your acceleration is directly proportional to the displacement, but it is a restoring force, you said. Therefore, it has to come back to this particular point. Therefore, it is minus a into y. Right? This is a very simple equation. This is written as m square equal to minus a, m equal to plus or minus ia. Are you familiar with this? Generally, we won't call it as a, we call it as omega or omega square. Then this is omega square, therefore it is I omega. Alright, when you have this, then the solution will be a some constant times of e power I omega plus b times of minus I omega. I can, therefore this is, what is your e power I theta? E power I theta is cos theta plus I sin theta. E power minus I theta is cos theta minus I sin theta. Therefore, that is why you get to know, he said that it is represented in terms of sin and cos. The periodicity, it comes because of that. Alright, it mainly comes from here, from the basic understanding that your acceleration is proportional to displacement. Alright. So this motion is called harmonic motion. The particle which makes this kind of motion is called harmonic oscillator. The particle which makes this kind of oscillation is called a harmonic oscillator. Yes, sir.
Sir, over there you have written m square is equal to minus omega square. So shouldn't m be equal to plus or minus I mod omega?
I?
Mod omega. Modulus of omega.
Yeah, no problem. You can have it. But if you look at this, right? How many roots you will have? How many roots you will have? Two roots. Yeah. And that is a reason. This I comes for this. There is no worry about this quantity. It is a frequency. This quantity is a frequency. Alright. So you need not to write modulus. This is a frequency quantity. It's always passes. Plus or minus, this minus I comes for this minus. M equal to root of minus I omega. You got the point? See, minus omega square. So this is root minus 1 omega plus or minus root of minus 1 is I, therefore it is plus or minus I omega. This quantity is frequency. So no need for this mod writing. The particle which makes this kinds of oscillation is called harmonic oscillator, right? We can do this slightly more, right? What is this? Y square equal to 4ax. What is this? Parabola. How it looks like? Alright, it is like this, or it is like this. Like this. Alright, and you define something called, what is this? It passes through focus. What is this? Lattice vector. And what is this distance? 4a or 2a? 4. Anyhow, you check it up. I don't know. Right? So we define what is a conic. I have a fixed point S and I have any other point P, x comma y. It moves in such a way that SP by PM is always constant, and this quantity is called eccentricity. Yes or no? E. What is the eccentricity for parabola? 1. Alright, you are all familiar with this. Right. Now I have a molecule A, B connected by something like a spring. Alright, it is like a spring. Therefore, this looks like this. Consider I have a small molecule diatom AB connected by a spring. Alright, the distance is x. So whenever, now I have now this is the physics problem. This is a rooftop. I have a spring. Alright, I connect a small mass mg. Alright, the spring will have what? Tension, right? Other than that, something called a spring constant. Alright, so it has a spring constant K. Alright, therefore I slightly pull and leave it, then it will vibrate like this. What is this motion? Harmonic motion. That's the harmonic motion, harmonic oscillator. This kind of thing is called the harmonic oscillator. It is a harmonic oscillator. What is the potential energy of this spring? Which is half. Excellent. It is a half k x square. So the potential energy is simply half k x square. What is x here? Displacement, elongation. let me call the original length as x naught. At any instant of time, I am elongating to x. Therefore, it is half k x minus x naught square. You agree with this? That's a displacement. You said x is a displacement. So, original distance is x. I am elongating it to original is x naught. At any instant, it is x. Therefore, the elongation is x minus x naught. Therefore, this is the potential energy. So, you agree, right? Any doubt about this? Nothing. Clear, right? So, that's all. My day is made. Right? Very simple now. Very, very simple. This is the mathematics that I need. Alright. So today, for molecules, all these can be worked out. Alright, there is something called force field energy. What is force field energy? Alright, suppose I have a molecule. Yeah, by the way, I will finish this and come back to the molecules. Now, when you have this half k x square kind of, what is this half k x square? Potential energy. But mathematically, how it looks like? No. Parabola. Excellent. Whether it touches 0, will go below 0? Right. Therefore, this is my k. And then there are a lot of maths one can work out on this. I am not going to talk about this. So, this is the, right? Now, the harmonic oscillator energies are quantized. The energies of the harmonic oscillator are quantized. The energy En equal to n plus half h bar. H is the Planck's constant. Omega is the frequency which we have seen here. And when n is quantum number, it's called vibrational quantum. And this is n equal to 0. N is equal to, even at n is equal to 0, right, there is an energy. That energy is half h bar omega. This energy is called 0 point energy. Very, very important concept. You will learn more about this in future. Therefore, suppose I give energy, I give electromagnetic radiation to this. I give electromagnetic radiation to this oscillator. Then what will happen? The molecule which are in this state will move from n is equal to 1, n is equal to 2, n is equal to 3. Therefore, from here it will go to this. From here this will go to this. From here it will go to this. So, if I give energy means what? I excite the molecule. This is basically electromagnetic radiation, EM. It's only the electric component. That is, only it is interacting with the E0 cos omega t or sin omega t, whatever the form that you want to take it up. Basically, it is E0 e power plus or minus I. Alright. Therefore, this simply make it as e power I omega t, that itself is fine. Alright. Therefore, this portion is going to interact with this molecule. Alright, and the molecule is excited. Therefore, a molecule will go from n is equal to 1 state to 2 state, 2 to 3, 3 to 4 and so on. This they don't want to be in the excited state. Therefore, a molecule will come from this state to state. Alright. Therefore, this is you will observe in certain electromagnetic spectral region. Right. In the case of a vibration, you will observe this in infrared region. This thing which is connected to this particular system or this particular model, you call it as vibrational spectroscopy. It's also called infrared spectra. So the origin of infrared spectra is basically it is a harmonic oscillator. The harmonic oscillator energies are quantized, and let's say n is the quantum number. Alright, the energy of the harmonic oscillator E equal to n plus of h bar omega. Then when the light shine, right, infrared shines, the molecule will go from n is equal to 1 state to 2 or 2 to 3, 3 to 4 and so on. Right, basically the change in the quantum number, right, delta n equal to plus or minus 1. This is called selection rule. This is called vibrational selection rule. Right, this you will see in vibrational spectroscopy, that is infrared. Right, there you will have a magnetic resonance spectroscopy NMR. I hope you have seen. Have you visited any lab? Yeah, hope you will get a time. You have seen. So, you hope you will get a time to see what is magnetic resonance and so on. So, what we started off with a harmonic oscillator, alright, and it has a K, that's a spring constant. Its potential energy is half kx square. I can plot the potential energy half kx square like this, then it is a parabola. The energy of this harmonic oscillator is quantized. This is the general expression. When I shine light, when it interacts with the electric component of the electromagnetic radiation, the molecule in the ground state will go to the excited state, first excited state, because delta n is plus or minus 1. That's a selection. And then they don't want to be in the excited state, they will relax back. Therefore, they get de-excited. So, therefore, you will observe energy. How do you observe energy? This is what it is. So, whenever you have so I have this is E0 ground state, this is my E1 first excited state. So, when I shine light, right, from here it will go here. And then they don't want to be in the excited state, always they wanted to come back to the ground state. This is given as a HNU. Alright. So, this is the very important understanding. This is called two-level model. Now, this energy, we have, this is a spring, we have seen that. Therefore, the energy difference between these two, alright, E0 to E1, E0 to E1 or E1 to E0, right, this difference is H omega or H nu, whichever you want to use, H bar omega. Therefore, your frequency omega, I will make it as nu, your nu is equal to 1 by 2 pi into root of k by mu. Right, this mu is called reduced mass. Because I asked you to consider a diatom, right, and diatom now A, it is some hypothetical atom A connected to spring with a constant K. Its mass is m1 and its mass is m2. Therefore, the reduced mass is 1 by mu is equal to 1 by m1 plus 1 by m2. Therefore, reduced mass is equal to m2 plus m1 divided by m1 m2. Therefore, mu is equal to m1 m2 divided by m1 plus m2. So, that is a reduced mass. Therefore, it tells you that I have a 2 atom, it vibrates. When it vibrates, it's not m1 m2 separately, as a collective one having a reduced mass mu, that reduced mass is making the movement. Alright, this quantity, therefore this this is the natural frequency. This is E0 ground state, it is going to the excited state. This is E1. When this interacts, alright, when light interacts, then it comes back, electromagnetic radiation comes back, first excited and it comes back, then the difference in energy is h nu. This frequency is given by 1 by 2 pi into k by mu. K is your force constant, mu is your reduced mass. Therefore, from this I can construct, these are all the requirements for me, right, to construct the potential energy terms, right. That is what I am going to do it here. So, I have what is called a stretch energy, that is I have a bond which is stretching and coming back, alright. When I have 3 atoms, now I told you about 2 atoms. When I have 3 atoms, I have A, here I have a B here, and I have a C here, then it can bend, alright, it can vibrate. So, this molecule will have a 2 stretching and 1 bending. So, this will have 2 stretch and 1 bending. Now, I can think of a collection of molecules. What is the collection of a molecule? I can have another atom, 4th atom, alright, a D, this is connected to like this. So, you will have another bending, another stretching and so on. Therefore, the molecules that you are thinking of, alright, the simple molecule which I can give you here is CH3. In addition to this, alright, A, B, C, D. Now, when this, with reference to this bond, the CD bond, it can also make a rotation. Therefore, what are the motions you have now? This CH can stretch, this can stretch, this can stretch, this can stretch, alright. This can bend, this can bend. More than that, about this bond it can rotate. About a bond it can rotate. About a single bond it can rotate. Yes, sir.
K and mu are here.
Yeah. K is your force constant. You are familiar. K is your force constant. Mu is your reduced mass. Now you have two masses, alright, and because you have a collective motion, it is not, M1 moves and M2, they are not independently moving. The entire system behaves like a one system which is moving. That is why you call it as a reduced mass. What is? No, that's what I said. Yeah, please, it's a good question. What he says is, what is K for a molecule, right?